Hello, my name's Tom Chambers. I'm an artist and I do various things, one of which is generative art. So lately I've been experimenting with self-organizing systems and I want to share with you some of the results of that experiment and my thoughts on how in the future we might be using these kind of systems more and more in our built environment as well as digitally. So something that I love and find fascinating is swarms. There's lots of names for this, but a good one is emergence, which means complex phenomena that emerge from many components in a system interacting with each other without any central control, also known as self-organizing systems. So examples are honeybees, where each bee has a specific role and they collectively manage the hive through thousands of tiny interactions with each other, passing information around. And social movements draw large numbers of people together to act in concert without anybody at the helm directing what they should do, where they should go, what they should say. So cities are a great example. There are exceptions, of course, but the successful ones tend not to have a grand master plan. They're grown piece by piece as people make a decision about where to live, where they want to shop, where they want to go to have fun. And all those decisions turn into an aggregation and the built environment, and that is the city. So here I'm starting with nature. This is how birds flock. When scientists were studying this, they were trying to find the leader bird until they modelled it, and they discovered that birds just followed a few simple rules that create these amazing shapes in the sky. And because flocking is made up of simple rules, we can simulate it. So these are those rules that we use to simulate, called Boids. We have separation. They want to stay away from each other, basically not bump into each other. Alignment, they want to go in the same direction as other birds. And cohesion, they stay close to the centre of the group to stay together as one mass. And here we have a simulation using those rules. I'll use the word agent in this talk to describe the individual components. And as you watch this, they cluster into groups forming patterns. So next time you see a flock of birds, think about these three simple rules. Follow the group, align and separate. No bird is in charge. And these rules are what I've based my experiments on. And one of the reasons we had to rely on hierarchical organisation in the past is because we didn't have efficient tools of communication. We had to rely on managers to get information up and down the chain and share it around. And now we're sharing data constantly with each other all the time, often without even having to actively actually do it. And we now have cheap enough hardware that we can make any object communicate with any other. Bricks could be embedded with communication chips that let them talk to other bricks. And robotics is not that far off. And the ability for bricks to be able to move themselves around little legs or actuate in some other way, communicate and talk and move together and move apart from each other is not a crazy pipe dream. So that brings me to my thoughts on what I'm calling organic design. So I'm definitely not the first person to come up with the idea of using self-organizing principle in design. There's lots of clever people thinking about it. This is just my experiment and contribution to the concept. So thinking about architecture, buildings are often made with regular forms. They've got straight edges from rectangular spaces. And this makes sense because that's the way that we've been able to manage our materials so far. But I think what we're missing is the organic element of the natural world. That's the way that trees or flowers grow to create organic shapes that are comforting and kind of feel nourishing spiritually. We're wired to appreciate those natural forms. They feel alive because they move in response to their conditions and they grow into the environment they're in. And when we look at an image like this forest, we can feel that sense of growth, the way that it's grown. And we have, in design, developed interesting tools to expand past the human factor. So parametric design is one. Designers set inputs to mathematical formulas that take advantage of the processing power of computers to create complex shapes and patterns like this building with this amazing swooping curve. But a person still has to come along and set those parameters and choose them and then alter them depending, to influence the output. And once the parameters are set, there's no interaction with the environment. It's all deterministic, from the start of the parameters. It's often beautiful, but it's rigid in a way. And so another similar, connected approach is generative design that allows a designer to specify a set of output criteria. So, for instance, generating a floor plan for a design for office space so that the walk from all the desks to the meeting room is within a certain distance. And what we're doing here is we're taking advantage of the computer's processing power to produce many, many options, and then we can measure which ones meet the criteria and which ones we can use. But it's still essentially brute forcing the problem. Try enough solutions and see if any work. Run a million simulations, subtracting material from a design, and see which one is lightest and still functions as a table or a chair. But with organic design, we can flip that. The designer can set a different kind of parameter. They set rules for each agent in the system, like don't go too close to your neighbor, follow the group, and so on. And the agents use these rules to choose where to go, independent of what else is going on in the bigger picture. And the result is emergence. The idea that we can model the way that organic systems like plants grow so that they fit the environment to their advantage, without any conscious intention or overall direction about whether it's right or wrong. So this is what happens when we take those same rules but put the flocking simulation into 3D. And so instead of each agent moving around, what I've done is each agent creates a child agent, and then that agent has another child. So it's recursively creating more and more agents, and they leave a path as to their history, where they go. And it quickly creates really interesting, complex patterns. So here are about the rules so that particles travel upwards. Plants do this, and it's called gravitropism. So some of these I could have drawn manually. That would have certainly saved a lot of time, but I want to build a system that is capable of producing completely different forms depending on the rules and environment. And this is the simulation run again, but using a slightly higher separation rule this time. So particles want to get away from each other more, and they start to twist out in an attempt to escape their neighbours. And by tweaking the rules that agents follow, it came out with this sort of crazy thing. And this probably, I don't know if this fits the criteria of inducing relaxing natural feelings, but you can see the way it creates shapes that are sort of going all over the place, sort of random, but also have an organic feel and rhythm to them. So a bit like a spider's web or veins like snaking around. And as I said, cohesion is one of the rules that agents follow in swarms. Agents want to stay together with the group. And when the groups meet each other, all the particles in the different groups want to be part of one big group. And so by adapting and tweaking like what these rules are, we start to get something in a form that people could be inside, essentially a building. So here you can imagine just being inside this structure. And now, so I've taken the same same code for the simulation. I've just used a different renderer, so you can imagine them as forms that you could be skyscrapers in a city. And of course, the key part of organic design is that it's able during the growth phase to respond to the environment. And what I did, I added a light-seeking rule. So plants do something called phototropism, and basically they grow towards the light. And because this simulation is made of agents that are like cells, the agents in the simulation can do the exact same thing. And the building can act like a whole organism that responds to the environment. So you can see in this one, on the far left, there's no light, there's no reaction to the light. In the middle, there's some reaction to the light. On the far right, the light, like seeking out light, becomes the most important rule for each agent. So you can see how that results in quite different outputs. And buildings that start out in the dark can start to grow into lighter spots, leaning around other buildings to soak up as much sun as possible. You can see how the second building shoots up because it's growing even taller more quickly to reach the light. And when it gets to the top, it grows into the space available. And I made a video here that shows how each agent in the system is seeking out the sun. If it's green, it's getting sunlight, and red indicates no sun. So it tries to react and find the light. And this is another rule that I've added to grow in response to other buildings. And here I've set the rules so the buildings want to be close together. Here it is in sort of skeleton form. So they grow towards each other while giving their neighbours a minimum space. So rather than dividing plots of land into individual blocks into rectangles, we could go beyond that by setting rules for how buildings grow. And so the space between buildings is dynamic depending on whatever rules they're following at that point, rather than having explicit boundaries. And in this one, we get a kind of double pattern. There's the spirals of the individual agents, and then the spirals of the collections of agents winding around each other. And so here I've set a rule so these buildings have a very strong attachment to attraction to each other. So they're sort of growing over each other like claws. And here we have the same thing again, but just with that attraction rule toned down a bit. So they're still growing towards each other, just a bit less intensely. And this is a kind of like imagining of like, what if we took that rule and we grew a whole neighborhood of buildings growing together. And here we go. So this is using the rays again to show like buildings trying to get away from each other. When it's red, that means they're too close. So when it's green, they've reached an acceptable distance away from the other building. And here we have that one again where they're growing apart. So what else? We talked about how we can add simple rules that allow buildings to adapt to their environments in all sorts of ways. I've talked about light and other buildings, but there's much more. The rules can be responses to people as well. So imagine a building that adapts itself over time to the way it's used. Where people congregate, the agents react to that locally and move themselves out the way, and agents close in on spaces that aren't used very much. So over time, the building is constantly shifting to what the needs of its users are. The designer doesn't need to know the exact purpose of the building. They just need to observe the environmental conditions it will be in and collect the data to input into the simulation that produces the design and adapts it over time. It doesn't throw away anything about the parametric or generative approaches. We can try different rules and variants of rules to see what works. And that's what I've been doing throughout this process, tweaking the system and tweaking the rules and parameters to see what emerges. It's kind of like hyper sped up gardening. Plant the seeds, shape the environment, create the right conditions, and observe the growth. Because it's actually as well as the rules themselves, it's also if you don't have the right amount of light or the right amount of warmth for a flower, it won't grow in a healthy way. And that's the same for a building. Like it might not be the building's rules itself that are the problem, but the environment itself that needs to be improved. And so you can really see the detail in these images of how complex the patterns become as the agents twist around each other. And here's what it's like bringing together the sun-seeking rule and the grow towards each other building rule. So both those at once, building a neighborhood. And yeah, here's that whole neighborhood from above. And the byproduct of generating using these rules, all the spaces and passageways that create interesting ways, changing shape and size and direction without having to be planned. And finally, one last thing, you can see how you can get something completely different by altering the parameters of the rule. So this flower-like building, where the agents group together like tightly, gets subsumed by another building that's trying to get as close as possible to the first one, effectively encapsulating it like a little cover. And that's it. So I hope you enjoyed this kind of lightning tour through this, and I hope it made you think a little bit about the possibilities of emergence in design architecture. I'd really like to know what you think about it, and if you've got similar work or you'd like to collaborate. And have a look at the website in the description. You can see all the photos and videos that I've included in this slideshow. Thanks very much.